Ever wondered how soap gets rid of oil and dirt? The answer lies in the chemistry of substances called surfactants. These are fascinating compounds that have a unique ability to reduce surface tension, allowing them to interface between water and oil or any other immiscible liquids. This remarkable trait stems from their molecular structure, which consists of a water-loving or hydrophilic head and a water-fearing or hydrophobic tail. Now, you might be wondering where you've encountered surfactants. Well, they're everywhere. From the soap in your bathroom to the detergents in your laundry room, even in the food industry and cosmetic products, surfactants play a crucial role. They're also key players in industrial processes, aiding in oil recovery, mineral processing, and many more applications. So ready to dive deeper into the world of surfactants? Buckle up because science is about to get fascinating. Not all surfactants are created equal. They come in different types, each with its own characteristics. Let's dive into the four major types of surfactants: anionic, cationic, nonionic, and amphoteric. Anionic surfactants, first up, are negatively charged. These are the most common type and are used extensively in detergents and shampoos due to their foam-producing qualities. However, they can be quite harsh, stripping away natural oils. Next, we have cationic surfactants. These carry a positive charge and are often found in hair conditioners and fabric softeners. They're great at reducing static and making hair and fabric feel soft and smooth. Thirdly, we have nonionic surfactants. These have no electrical charge, making them very gentle and great for sensitive skin. They're often used in baby products and cosmetics. Lastly, there are amphoteric surfactants. These can carry either a positive or negative charge depending on the pH of the solution they're in. They're very gentle and are often used in combination with other surfactants to boost their performance. Now, how do we classify these surfactants? That's where the hydrophilic-lipophilic balance, or HLB scale, comes into play. This scale, ranging from 0 to 20, measures a surfactant's solubility. A low HLB value between 3 and 8 indicates that a surfactant is more oil-soluble. These surfactants are typically used to form water and oil emulsions. On the other hand, a high HLB value between 12 and 15 indicates that a surfactant is more water-soluble. These surfactants are typically used to form oil and water emulsions. Understanding the HLB scale allows us to predict the behavior of a surfactant in a solution, which is vital in many industries, including cosmetics, pharmaceuticals, and food production. Now that we know the types of surfactants and how they are classified, let's explore how they behave in solutions. Ever observed how a drop of oil disperses in soapy water? That's micellar solubilization at work. Let's unwind this term a bit. Micellar solubilization is a unique process where surfactants, substances that lower the surface tension of a liquid, form micelles. These micelles are tiny spherical structures that can encapsulate and dissolve substances that are ordinarily insoluble in water, like our oil droplet. This is why your dish soap can tackle that greasy frying pan with ease. Now, for micelles to form, surfactants must reach a certain concentration known as the critical micelle concentration, or CMC. Below this point, surfactants are dispersed as individual molecules. Cross this threshold and voila, we have micelles. Now, let's sidestep to a couple of intriguing points known as the Krafft and cloud points. The Krafft point is the temperature at which a surfactant, initially in a solid state, starts to form micelles. Beyond this temperature, the surfactant becomes more soluble and the CMC decreases. Think of the Krafft point as the surfactant's wake-up call to spring into action. On the other hand, the cloud point is the temperature at which the surfactant solution becomes cloudy due to the formation of larger micelle structures. This is because at higher temperatures, the hydrophobic or water-hating part of the surfactant prefers to stick together rather than interact with the water. Both the Krafft and cloud points are crucial in determining a surfactant's behavior, especially in applications like detergents and emulsions. For instance, a detergent with a high cloud point would be more effective in hot water, while one with a lower Krafft point would dissolve more readily in cold water. Understanding these concepts gives us a better grasp of how surfactants operate, and more importantly, why your dish soap is such a champ at tackling grease. With these concepts in mind, we can now delve into the fascinating world of monolayers. Imagine a layer of molecules so thin that it's only one molecule thick. Welcome to the world of monolayers. Now, let's dive deeper into this world. Monolayers can be broadly classified as soluble or insoluble. Soluble monolayers are those where the surfactant molecules in the monolayer are in equilibrium with those in the bulk solution. This means the surfactant molecules can easily move between the solution and the monolayer. On the other hand, insoluble monolayers are those where the surfactant molecules are not in equilibrium with the bulk solution. Hence, the molecules cannot freely move between the monolayer and the solution. Understanding how these monolayers behave is crucial in surfactant chemistry, and here's where the Gibbs equation comes in. Named after the American scientist Josiah Willard Gibbs, this equation is a mathematical representation of the behavior of soluble monolayers. The Gibbs equation states that the change in surface pressure of a monolayer is equal to the negative of the change in the area per molecule at constant temperature and number of molecules. It's represented as dP equals sine GdA. Here, Pi represents the surface pressure. Gamma is the surface excess, which is a measure of the amount of surfactant in the monolayer, and A is the area per molecule. The Gibbs equation helps us understand how changes in the area per molecule, for example, due to compression or expansion, affect the surface pressure. It also gives us insights into how surfactant molecules pack together in a monolayer and how they respond to changes in their environment. So, soluble or insoluble, monolayers play a critical role in surfactant chemistry. They help us understand how surfactants behave at interfaces, how they reduce surface tension, and how they aid in processes like emulsification and foaming. Monolayers may be thin, but they play a big role in surfactant chemistry. Surfactants don't just work in liquids, they also interact with solid surfaces in fascinating ways. Let's delve into the concept of adsorption at solid interfaces. It's a process where molecules from a gas, liquid, or dissolved solid adhere to a surface, creating a film of adsorbate on the adsorbent. This process is influenced by the nature of the adsorbent, and the interface between them. The behavior of adsorbate molecules at solid interfaces can be described using adsorption isotherms, which are graphs that show how the amount of adsorbate on the adsorbent changes with pressure or concentration at constant temperature. Two of the most commonly used isotherms are the Langmuir and Freundlich isotherms. The Langmuir isotherm assumes that adsorption occurs at specific homogeneous sites within the adsorbent. It also assumes that once a site is filled, no further adsorption can take place at that site. This isotherm is particularly useful when dealing with systems where the adsorbate is in a gaseous state. On the other hand, the Freundlich isotherm is an empirical equation that does not assume a homogeneous surface or specific adsorption sites. Instead, it suggests that the amount of gas adsorbed increases infinitely with pressure, and that different sites have different affinities for the adsorbate. This isotherm is generally applied to systems where the adsorbate is in a liquid state. Understanding these isotherms and the concept of adsorption at solid interfaces provides valuable insights into the behavior of surfactants. It allows us to predict how surfactants will interact with different surfaces and under varying conditions, influencing everything from the efficacy of cleaning products to the behavior of industrial processes. Surfactants are truly versatile. They can interact with a variety of surfaces and influence a multitude of processes. So there you have it. The world of surfactants is much more than soap bubbles and cleaning agents. We've journeyed through the complexities of surfactant classification and the HLB scale, unraveled the mysteries of micellar solubilization, Krafft and cloud points. We've delved into the intricacies of soluble and insoluble monolayers, explored the Gibbs equation, and investigated adsorption at solid interfaces. We've even navigated the complex landscapes of Langmuir and Freundlich adsorption isotherms. Remember, these concepts are not just theoretical constructs. They find applications in fields as diverse as pharmaceuticals, food production, cosmetics, and more. Understanding surfactant chemistry can open doors to a multitude of opportunities. The world of chemistry is vast and exciting, and we've only just scratched the surface. So, if you love peeling back the layers of the scientific world as much as we do, hit that subscribe button. Subscribe for more because you won't find me later.